So let's talk about transformers and power transmission. So this is actually a very, very, very important aspect of electricity and magnetism that's only been known since about 1885, maybe a little bit before that, when Nikola Tesla really pushed the idea. So here's the idea. When we try to transmit power through long power lines, we always suffer a loss. We suffer a loss of power due to what's called I squared R heating. And that's because every wire, no matter what we make it of, is going to have some resistance, because that material has a resistivity. And that means the longer the wire, the more the resistance. So if we've got a wire that's 10 feet long, nobody cares. If the wire is 1,000 miles long, leads to a problem. And so we get this heating associated with I squared R. So notice that this heating will become smaller if I can make the current really small. So all we need to do is just transmit power at a really low current. But if we try to do that with DC, we got a major problem. Because low current means we don't have very many electrons doing anything. And with DC power, that's what you need. You need electrons doing stuff. So if we've got a small current, there's no reason to transmit the power anyway because there's not very much power. So alternatively, what we can do using alternating current is we can step up the voltage. Now what's beautiful about this is that using AC current and using electromagnetic induction, when we bump up the voltage, the power has to remain constant. Now the power that we're transmitting is IV, current times potential difference. That has to remain constant. So if we bump up the voltage, say by a factor of 100, then what has to happen in order for I times V to remain the same? Well, it means we got to bump down the current by a factor of 100. Now, when we send that into the transmission line, now I's down by a factor of 100. So that means I squared R is down by a factor of 10,000. So this is very, very, very useful. And in standard communities, you'll use a step-up transformer like this to bump up the voltage from a standard household at like 120 volts all the way up to standard transmission voltage, 450,000 volts. And that's the way that it works. All right, so let's look and see how a transformer is built. It's based on the idea of electromagnetic induction, but we got to do a little bit of stuff to make it feasible. So here's what we're going to do. We're going to have our primary, and we have the wire come in, and this is what's carrying the current, and he wraps around an iron core. All right, we need to use iron or some other soft ferromagnetic material. It needs to be magnetic, but it needs to also be very transient in its magnetism. So it needs to just listen to whatever an external magnetic field is telling it to do. A permanent magnet would not work as the core of a transformer. So let's see why. All right, we've got this incoming current. We wrap it around part of the iron core some number of times. The number of times I'm going to call N sub P for number of primary turns. All right, and then we send it out. Now, this current is going to come through, and because it's a current, it's going to generate a magnetic field. Now, what happens to that magnetic field? Well, this is a soft ferromagnet. So if the magnetic field associated with this guy is pointing up, then the whole iron core will generate a magnetic field that circulates around with the magnetic field that the primary is asking it to use. And look what happens. Now there's a magnetic field over here that's threading the secondary part of the circuit. Now, just leaving it that way, nothing happens. All right, that'd be like DC. All right, we got a magnetic field. What do you want? There's a magnetic field. In order to use electromagnetic induction or the Faraday-Lentz law, we need to change this magnetic field. And the way that we're going to do that is by changing this current that's going into the primary. And we're going to do that using AC. So we're going to change it 60 times per second. Now what that does is it changes this magnetic field, therefore changing that magnetic field and changing the flux of that magnetic field through this part of the circuit. So through electromagnetic induction, what that does is it generates a current over here. So we had a current over here. Changing that current changes the magnetic field circulating through the iron core, and then that changes the magnetic flux running through here and then through Faraday lens. That generates a current over here. And it's a bit to think about, but it kind of makes sense. You know, it takes a minute to really get into all that, magnetic field going through here, whatever. But what ends up being the case is that the potential difference between these two parts of the wire is proportional to how many wraps of wire we have. And that means the ratio of the secondary potential to the primary potential is equal to the ratio of the number of turns, and it's a geometrical fact, how many times did you turn it around, over in the secondary side to the number of turns on the primary side. So that means that if I come in and I only wrap once, and over here on the secondary side, I wrap 100 times, then the voltage over here on the secondary side will be 100 times bigger than the voltage over here on the primary side. And that means that the current's going to be 100 times smaller. And so this is called a step-up transformer because it steps my voltage up by a factor, in this case, of 4/3. Okay, maybe this isn't a very good step-up transformer, but whatever. And then I'll step it up. I'll transmit my power over how many hundreds of miles I need to from the power plant to the houses. And then at the houses, I run this guy backwards, step it on back down, and I'm good to go. Again, one of the wonders of AC power that we could not get from the old DC system. And that's transformers and power transmission.